We've talked briefly about the idea of solving a system of linear equations by doing some manipulations to that system until you reach a form where you can actually read the solutions off. We saw that there were three types of manipulation which you can do to a system of linear equations. We also saw the effect of these manipulations on the augmented matrix of the system of linear equations could be described by three different types of row operation. But the point was to find the solutions, if there are any, of the original system of linear equations. And that raises two questions. First of all, how do we know that the solutions of the system of linear equations you end up with after you've done all these manipulations are actually the same as the set of solutions to the original system of linear equations? Secondly, what kind of simple form should we be aiming at from which we can read off the solutions, even to a quite complicated system of linear equations? In this video, we're going to try and answer both of these questions, beginning with the result, which can be phrased as saying row operations don't change the solutions to a system of linear equations. Specifically, here's the statement of the theorem I'm going to prove. Suppose that you have an augmented matrix A', B' that results from doing a sequence of row operations to another augmented matrix AB. Then, the set of solutions to the matrix equation you've ended up with, A'x equals B', is the same as the set of solutions to Ax equals B. Now, in order to prove this, it's enough to do the case where A', B' results from doing a single row operation R to AB. That's because if doing one row operation doesn't change the set of solutions, then neither does doing 2 or 3 or 4 or however many. So we can assume that A', B' arises by doing a single row operation R to the augmented matrix AB. Well, we know how to describe the effect of a row operation on a matrix. It's equal to the effect of left multiplying by the appropriate elementary matrix. So in the case where A', B' arises from doing R to AB, well then A' would be the same as R of A, which is equal to R of I times A. Equally, B' is equal to R of B, and that's R of I times B. Let's write that in. So this is equal to R of I times B. I'm underlining that B to emphasize it's supposed to be a bold, a vector B. So here, I is the identity matrix of whatever appropriate size. Well now, let's look at the condition for a vector v to be a solution of the original matrix equation. So by definition, that's true if and only if. So v is a solution if and only if AV is equal to b. That's what it means for v to be a solution of the original matrix equation AX equals b. But that's true if and only if R of I times A times v is equal to R of I times b. You can go from this line to the line below it by left multiplying by R of I, but you can go from the second line back to the first line by multiplying by the inverse of R of I. Remember, we showed that every elementary matrix was invertible. But we've just observed that R of I times A is A' and R of I times B is B'. So the second line is equivalent to the third line, which says precisely that V is a solution of the matrix equation A'x equals B'. Altogether, we've shown that V is a solution of Ax equals B if and only if it is a solution of A'x equals B'. In other words, that doing a row operation to an augmented matrix does not change the set of solutions to the corresponding matrix equation. So that justifies our method of finding the solutions to a system of linear equations, which was do a bunch of row operations to the augmented matrix until you get the augmented matrix into a format where you can just read off the answers. So where the equations are simple enough that we can actually see directly what the solutions are. But what is this form from which we're going to be able to read off the solutions? So what is this simple form of an augmented matrix, which is so simple that we can actually just read off the solutions of the corresponding system of linear equations? Well, for us, that form is what's called row-reduced echelon form. And to describe row-reduced echelon form, I need the concept of a leading entry. So here it is. A leading entry in a matrix is the first non-zero entry in a particular row starting from the left. As an example here, the first row has leading entry 2 in column 2. The second row doesn't have any leading entry at all because it doesn't have any non-zero entries. So a given row of a matrix may or may not have a leading entry, and if it's all zeros, then it doesn't have a leading entry. But if it's not all zeros, then the leading entry is the leftmost non-zero entry. We'll often say LE as short for leading entry because it's a phrase we're going to use a lot. Having described the leading entry, we're now ready to define row-reduced echelon form. The definition has 4 parts. A matrix is in row-reduced echelon form, or RREF for short, if it satisfies the following 4 conditions. First of all, every leading entry must be equal to 1. Secondly, any zero rows, so any rows which only have zeros as entries, must be at the bottom of the matrix. Thirdly, if a column contains a leading entry, every other entry in that column has got to be 0. And finally, for every I, if there's a leading entry in row I and a leading entry in row I plus 1, then the leading entry in the row I plus 1 must be to the right of the leading entry in row I. So as you move down your matrix, the leading entries must go to the right. Let's see some examples. I've copied at the top of the slide here the definition of row-reduced echelon form, and we're going to look at some examples of matrices which are or are not in row-reduced echelon form. The first matrix here is not in row-reduced echelon form. Pause the video and look at the definition and figure out for yourself why it isn't in row-reduced echelon form. Okay, of course, the reason is that this matrix has an all-zero row, but the all-zero rows are supposed to be at the bottom, and here the all-zero row is not at the bottom. There is another non-zero row below it. Next example. This matrix is not in row-reduced echelon form. Pause the video and decide for yourself why not. The answer here is that row 1 has a leading entry, and that leading entry is 2. But in a row-reduced echelon form matrix, leading entries must be equal to 1. Thirdly, again, pause the video, decide for yourself why it's not in row-reduced echelon form. The answer this time is it doesn't obey the 4th condition. The leading entry in row 2 must be to the right of the leading entry in row 1 if your matrix is going to be in row-reduced echelon form. But here, the leading entry in row 2, which happens in column 1, is to the left of the leading entry in row 1. Moving on to this matrix here. This time, this matrix is in row-reduced echelon form if and only if beta is equal to 0. The reason for that is that row 2 contains a leading entry right here. This 1 in row 2 is a leading entry. Condition 3 for row-reduced echelon form is that all entries in the same column as a leading entry must be 0. So if this is going to be in row-reduced echelon form, then beta must be 0, because that's an entry in the same column as a leading entry, namely the 1 in row 2. Every other part of the definition of row-reduced echelon form is fine always. All the leading entries are 1, because there are 2 leading entries, one in row 1 and column 1, and that's 1, and 1 in row 2 and column 3, and that's also 1. All 0 rows are at the bottom. Well, there aren't any 0 rows, so condition 2 is fine. Condition 3 we've discussed, and that's fine if and only if beta is equal to 0. And condition 4, well, the way that applies is it tells us that the leading entry in row 2 must be to the right of the leading entry in row 1, and that's correct because the leading entry in row 2 is in column 3, which is to the right of column 1, where the leading entry in row 1 is. Finally, we have an example of a matrix which is in row-reduced echelon form. The leading entries are, let's highlight them. So we have a leading entry right here and here, and both of those leading entries are equal to 1. There is a row of zeros, but it's at the bottom, so that's fine. That's condition 2. Condition 3, every entry in the same column as a leading entry must be 0. So if we look at the columns of the leading entries, that's these entries here and these entries here, and you can see they are all 0. So condition 3 is fine. Condition 4 says that if row I and row I plus 1 have a leading entry, then the leading entry in row I plus 1 must be to the right of the leading entry in row I. The only two rows with the leading entries are 1 and 2, and you can see there that the leading entry in row 2 is to the right of the leading entry in row 1. So we're fine there. And just as a further comment, if I added in some more 0 rows, like adding this, like this would still be in row-reduced echelon form. So the matrix I've just obtained by adding an extra row of zeros is still a legitimate row-reduced echelon form matrix, because the 0 rows are still at the bottom.